Good day. About 50 years ago, I was a student and worked with Gradstein-Rizhik famous tables of integrals and series. Maybe at first time I looked on Meyer G function, this table. Oh my God, who can understand this horrible monster? So happened that in future years I worked a lot with this monster, and right now we have in Mathematica system implemented Meyer G function. Why it is a monster? I will show later. But we have simple, I call functions like sine, cosine, or Bessel function and other, and they include parameters and maybe one or two variables. But if we go to more complicated function, to hypergeometric functions, we see lists of variables. Hypergeometric PFQ function, it has two lists of variables, lengths P and Q. It is a very big function which includes many particular cases, including these elementary functions. And I can call this function a monster. Mathematica got implementation of these functions many years ago, and Bessel function, particular case of this hypergeometric, but Bessel K is not case completely, because Bessel K function with zero parameter, it is not belongs this hypergeometric. For description this Bessel we need more complicated. We need in Meyer G. And you see definition. You also see products of gamma functions, and it is four groups with arbitrary lengths Mn per Q. And in particular, this function includes about 100 named functions. And maybe all life I collect tables of these functions. This is my first book, was published about 40 years ago. And right now it became, today I had from very known professor, classical book. And it has table of this Meyer G. But currently I have 4,000 cases, and they can convert to Meyer G form in Mathematica system. What does it mean? It means that we can somehow forget and ignore names about 100 functions and work with Meyer G, because Meyer G accumulates different functions like exponential type, algebraic type, piecewise, and others. Yeah. Let's look on cases. We can evaluate these cases. And Meyer G is used in integration, as I mentioned, uniformity, because basically we can translate function into Meyer G form with Meyer G reduced, you see, in 29 right now. And this Meyer G inactive, appeared inactive Meyer G. But if we activate, we return back after function expand. Yeah, and in situation of these examples, you see several examples only. Right now, we are working to implement huge amounts of new possibility for integration. and for Laplace transform, for inverse Laplace transform, because in principle, if we go, where is this Laplace transform? You did not include, yeah?
It's at the end.
Yeah. Okay, if we make Mellin transform from Meyer G function, we will get a product of gamma functions which you saw. And if we use the convolution theorem, we need to multiply these products with other products, gamma function. For example, we had from one original function 5, from other 10, together 15. And again, we save the same class. We will have Meyer G with 15 functions, and we need to return back to original using residue theorem. This is main engine of such method, which implemented is System Mathematica. And I prepared very large talk, but here we can discuss details, and I can show demonstration how 4000 converts, how work integration in private talks with those who are interested. We have other monster in our system connected with differentiation. And people does not know that there exists uniformity, huge monster in differentiation, which also cover a lot, each operation in differentiation. What kind of operations we have? For example, derivative order m from composition order n, or series expansion, series from series, inverse series. Physicists permanently use these procedures and try to find formulas in handbook. But all these formulas can be described by using this one huge monster by name Bell Y. And Bell Y we implemented about 5 years ago. And this is a main specialist in Bell Y. Then McDonald, he made very elegant general solution and numerical evaluation, which was implemented instead other one, which we had. It was in time when he was student in internship. And I will give him opportunity to continue talk.
Okay, right, so in the literature, if you look on Wikipedia or for Bell polynomials, you will probably be more familiar with this first one, this partial Bell polynomial with these indices n and k, and then just a list of input variables. So this is Bell. So this partial Bell polynomial is notable for several properties, but the one we'll discuss today is its use in differentiation of composition of functions. So this comes, this shows up in Feda-Bruno's formula, which is, why is this not? This slide's not.
Does not go?
Yeah. Let's see what happens.
Try other way.
Well,
Make the magnification smaller.
yeah, that's.
And then open up and see the
There we go. Thank you. Yeah, let's go to 150. Okay, so we all remember the chain rule from calculus for differentiating a composition of functions. And so in Mathematica, we can do that symbolically. And so to generalize the chain rule, we have kind of two directions. We can either allow higher order derivatives, which is what we'll do now, or later we'll see what happens if we allow composition of more than just two functions. So if we allow higher order derivatives, then this generalization of the chain rule is known as Fay-de-Bruno's formula. And so here you see one way of expressing Fay-de-Bruno's formula is through the sum involving these partial Bell polynomials. So here's what it looks like for the third derivative of f of g of z. So this is our implementation of Fay-de-Bruno's formula. And here is just Mathematica d function. And they give the same thing, which is good because otherwise Fay-de-Bruno died in vain, I guess. He didn't actually die due to this, I guess. Anyways. The Wolfram language now actually, thanks to Devendra, did he show up? Is he here? He might be coming later. Now uses Fay-de-Bruno's formula for if we input an unspecified higher order derivative of a functional composition. So here we're taking derivative of f of g of x, but we're taking the nth derivative where we don't know what n is, but we still output this formula based on Fay-de-Bruno's formula. But if we generalize the chain rule and that otherwise speaking about by adding a composition of a third function, we see the results get kind of unwieldy because we're basically applying Fay-de-Bruno's formula a second time, which adds in another summation, and these formulas quickly become kind of useless. So that's why we have these generalized Bell polynomials. So here we input a matrix to our Bell Y function, and one definition you'll see is this, very complicated summation, and you'll notice this fabulous Bell Y pun I did in my table naming convention. So you'll see the output here. So another Bell Y pun is, why does it have this kind of crazy definition? Because really it was reverse engineered to express the nth derivative of a composition of m functions. So basically it's what happens if you apply Fay-de-Bruno's original formula m minus 1 times. So the kind of, the thing to know about these generalized Bell Y functions is that if you put as input these derivatives of functions evaluated at these compositions of functions like this, then you get the nth derivative of the composition of functions. So this generalized Bell polynomial generalizes the chain rule in both ways. You can have arbitrarily high derivatives and arbitrarily deep compositions of functions. So here we make a table by just doing our straightforward higher order derivative using the d function. And then we can see using these generalized Bell polynomials, we get the same thing for these higher order derivatives of compositions. You also might have noticed a slide ago there was kind of an intermediate generalized partial Bell polynomials, which we won't really talk about today, but let's make this smaller.
Click the title once, then scroll down.
Yeah, there we go. I was okay, this is. These can be defined in terms of this larger general Bell polynomial. So the last thing I'm going to talk about is kind of a quick way to compute these generalized Bell polynomials using kind of their meaning as this means of differentiating these compositions of functions. So, thinking of the kind of the definition of these polynomials in terms of differentiating the composition of functions, we can notice that composition is associative. So we can really split up the composition of functions any way we want. So we can, instead of having m functions, we can have, here we have, it looks like p functions, or yes, where we group the first m1 together, then we group the next m2 together, and so on. So that gives us this functional identity, where we're just recursively using this definition of Bell Y on these submatrices. So in terms of a means for computing computing Bell Y, looks like we're going to make this smaller. Yes. Right. We can basically cut the partition this composition of functions into two equally sized sequences of functions. So f1 through fm over 2, and then fm over 2 plus 1 to f sub m, and apply this functional identity. And so this suggests a recursive program for computing these generalized Bell polynomials. Let's see. So basically we can pad the matrix with these columns that represent the identity function, since if you compose with the identity function, you're not changing anything until we get to a power of 2, until we get m as a power of 2. And then we have an implementation of Feda-Bruno's formula for a matrix having exactly 2 columns. That's this line here. And then we apply Feda-Bruno's formula successively until we're down to just 1 column of the matrix. And then once we're at the last column, we take the last element of that column, and that's the nth derivative of our composition of m functions. So if we run this little function here, then we can have this pretty big random matrix, and we should get the same result with this kind of ad hoc Bell Y function, and eventually the Mathematica function should give the same thing. Good. Okay, so I think Oleg wanted to talk a little bit more about.
And I want to add very important notes. You just saw that Bell Y satisfy compositions rules. And if instead with Bell Y we use Marichev transform, it is integral transform, like in particular Hankel transform, fractional integral, Laplace transform, inverse Laplace transform, Stiltiès transform, Meyer, and many other transforms classical transforms. All these transforms is integral transforms, is Meyer-G transform, cases of Meyer-G transform. And inverse to these transforms also Meyer-G type transforms. We studied this in this book, which was published about 30 years ago. Kilbas, Samko, Kilbas, Marichev. Fractional integrals and derivatives. Chapter 36 includes theory of these compositions of Meyer-G transforms. So again, for example, we can take normal distribution. It is also not normal, how to say, no, usual distribution with exponential function. And exponential function consists corresponds to one gamma function. Exponential function in my language, Meyer-G language, corresponds to gamma function. If we take composition of this, we produce product of these gamma functions. This product you can see inside of definition Meyer function. So composition will be again a Meyer transform, and all rules in sense composition, decomposition, inversion for this Meyer transform similar to what we hear right now about Bell-Y. So basically we have two monsters. One cover integration, other differentiation. And you did not talk about examples like how to evaluate inverse series using Bell-Y, how to evaluate composition of series or ratio from series and many inverse series and many other operations. Function, integrity function. We can make derivative of this using Bell-Y. We can expand in series. Everything can be doable. We have formulas which not presented in talk, but you can find in my collections. Thank you.
What does that say, Oleg?
Thank you very much.